Today I'm going to talk about practical uses for memory visualization. My name is Ulf Frisk, and I'm going to start with a short introduction to my previous work and also some background. Then we'll jump straight into what the PCI leech and the memory process file system is. Then we'll talk about two different use cases. First, how I used an earlier version of the software in order to find a total meltdown in Windows 7. Then we'll have a look how other people have been using modified versions of my software in order to do hardware-assisted cheating in games. After that, we'll go more in depth. We'll have a look at its capabilities, its API, the design, and the plugin functionality. Throughout the presentation, I will do demos, lots of demos, live demos. So let's hope everything is working. My name is Ulf Frisk. I'm working as a pen tester by day in Stockholm, Sweden, and I also try to do some security research by night. I'm the author of the PCI leech Direct Memory Access Attack Toolkit, which I presented almost 3 years ago at DEF CON. I found it's a really low-cost piece of hardware that was able to do direct memory access, DMA, over PCI Express. It didn't require any drivers on the target, and with this really low-cost piece of hardware, I was able to do well over 150 megabytes per second reading the main memory of the target computer over PCI Express and also writing to the memory. Unfortunately, this piece of hardware, even though it was really fast and low cost, it only was able to access memory below 4 gigs since it only supported 32-bit addressing. But at that point in time, that was not really a big problem since I was able to successfully attack most major operating systems anyway. Operating systems improved, and also the 4 gig limit was very boring, and this hardware, it became really popular, so it's sold out as well. So that's why I introduced public FPGA-based DMA attacking at the CCC a little bit over 1.5 years ago. Everything that I've been doing up until now, it's 100% open source, and everything is available on my GitHub page. But today, we'll have a look at the memory process file system, which is a memory analysis tool with a strong Windows focus. It allows you to visualize in-memory objects as files and folders in a file system. It comes with a C and Python API, and if I look at its multi-threaded core together with the native C code and some intelligent parsing in there, it's really fast. It also comes with a wide range of memory acquisition methods, not just the hardware-based ones we are talking about earlier on, but also software-based ones. So let's do our first demo for today. Let's mount a memory dump image created by Matt's awesome dump it tool. Let's mount it by double-clicking on it and do some really easy point-and-click memory forensics. So this is a memory dump image. It's 32 gigs big. So let's have a look at it. Let's analyze it. Let's double-click on it. It says it's mounted. And if we click into the M drive as it's mounted as, in the root folder, you see the pmem file, which is basically a copy of the physical memory. It's not really interesting if you're mounting a memory dump file as I'm doing now, but imagine if you're acquiring memory using the FPGA hardware, for example, or acquiring remote memory. We have a status directory which contains various configuration options, and but more interestingly, we do have the names folder which contains each process on the running system as a directory. Just click into. Let's click into the Explorer directory, and in each process directory, we do have a couple of files that we can have a look at. We have the base address of the director table base, CR3. We have the memory map, which is gained by walking the actual page tables that the CPU uses. And this is all done by parsing physical memory. And we also try to auto-identify what this memory is, if it's, for example, a heap, or if it belongs to some process explorer in this case. We also do have files for the entire virtual memory. Just open it in your favorite text editor, have a look at it, search for stuff in the memory, or if you're using FPGA hardware, you can hit save as well, and then you will write to virtual memory of that process, and it will be reflected down into physical memory. We have a couple of subfolders as well. We have a Python subfolder, which allows any user to code their own Python plugins quite easily and just drop the Python plugins in the program folder of the file system, and it will show up. And in this case, it provides like a small Python module, provides easy access to the eProcess structure and in the kernel, and we can just have a look at it by just clicking on files. More interestingly, we do have a modules subfolder to each process as well. And here you see all the loaded DLLs in the process, and you can analyze them live by just clicking into the subfolder. We can have a look at its exported functions, imported functions. Here we see the exported functions, where the function names and the memory address they are exported at. We have a look at the imported function as well. We can have a look at sections, for example, executable sections, text-only sections, and things like that. But if we wish to do edits of a section, we can also go into a subfolder. We can open it in the favorite text editor, whatever, and have a look at it if we so should wish. So let's have a quick look at it. Just. I should disable sound here. Yeah, this wasn't backed by physical memory, but if it's backed by physical memory, we can click into it, have a look at it, and we can actually edit the binary data, and we hit save, and it will be reflected down into memory if you're running with the FPGA devices where we have write capabilities. So let's continue. So doing analysis with a hardware device, it's really powerful. And in this example here, I do have an analysis computer, which is connected over USB 3 onto a really big Xilinx FPGA development board. There exist smaller boards as well, as we will see later on. And then you have PCI Express to the ThinkPad or Express card in this case. In order to read and write memory of the target system, I do in software on my analysis computer construct a PCI Express transaction layer packet. PCI Express is packet-based. I construct a memory read packet in this example. I wrap it in some extra metadata, which allows me to transmit it over USB 3 onto the FPGA. The FPGA then takes the PCI Express transaction layer packet, unpacks it, and put the raw TLP packet on the PCI Express of the target system. Once the PCI Express packet reaches the root complex of the target system, it sees that it's a read packet, memory read packet. So it reads from the physical memory of the target system and responds with a PCI Express transaction layer packet, which is a completion packet in this case, which contains the actual data read. And it responds with it back to the FPGA. And the FPGA forwards it back to the analysis computer. Writing works pretty much the same way, and this is really powerful. So let's continue to a couple of use cases. First, have a look at how I used an early version of the memory process file system in order to locate a total meltdown in Windows 7. It was a local privilege escalation vulnerability, which allowed any user to escalate the kernel trivially. It allowed arbitrary physical memory reads and writes at gigabytes per second. It only affected Windows 7 and 2008 R2, and it was something that was introduced in the meltdown patches from January last year. But it looked like it was patched in March last year, just before I found it. And I didn't see anything in the release notes from Microsoft, the MSRC, and I thought that was really strange, since they usually do give some credit to researchers or anyway put up a CV at the, but they didn't do this for this one. So I wrote them an email and told them I want to publish a blog entry about this. I found this really interesting. Is it okay? And they were like, yeah, let's check with our engineering team. And they responded the day afterwards and was like, yeah, it's totally okay to publish this blog entry. And in order to make it a little bit more interesting, I decided to publish a proof of concept as well. And the only problem was it wasn't fixed. And I released a trivially exploitable kernel 0-day with the permission of Microsoft. It was actually fixed if you were running with administrative privileges or if you were running as system. It was, however, not fixed if you were running as a normal low-privileged user. And since I ran everything in my test case as admin, I like to run stuff as admin on my test systems, I didn't spot this one, and neither did Microsoft beforehand. Anyway, really lucky here. They managed to scramble, and they came up with an out-of-band patch for the kernel itself just 2 days after I released my initial blog entry. And I think that's really super fast response time for doing stuff in the kernel. So really thank you to Microsoft for that one. But let's do a demo. Let's show how I came to find this total meltdown vulnerability. Let's locate it by looking at the memory map we had a look at a while ago. And in there, we'll see that the PML4, which is the topmost paging structure in the page tables, its self-referential entry was mapped straight into user mode. So I should have a vulnerable virtual machine here. So let's start it. Let's mount the memory process file system. I'm cheating a little bit here today since I'm using the actual vulnerability to mount the file system. When I was researching this, I was using the FPGA hardware. But once we have the file system mounted, we can click into some folder, for example, a CMD folder, and have a look at this memory map. In here, it looks kind of normal. It identifies some heaps and some binaries, and this is how it should look like. So nothing strange here until I scroll down at the end. I see a lot of addresses starting with 4 Fs here, which are read, write, execute, but they are not supervisor, so they are not kernel here. And addresses starting with lots of Fs, they're traditionally reserved for the kernel itself. They don't have to be really, according to Intel, but in Windows they should be reserved for the kernel. And this is really strange that I see these memory addresses in my process memory space. So what is going on here? I was also able to dump memory at very high speeds. So let's wrote up the proof of concept. I wrote it for my PCLH program. So let's try to dump the memory of this vulnerable system. And dumping memory, it's quite fast. I can dump memory at around a couple of gigabytes per second here. And I was also able to execute the evil kernel implants and insert them into the kernel. If it's, yeah. Code execution here, I've inserted my kernel implant in the kernel just like that. So what is going on here? I mean, this clearly shouldn't be the case. And let's have a closer look at it when we have the file system mounted here. So let's go into folder of a process, the CMD, and let's have a look at the 2 different PML4, the 2 different topmost page tables, since the meltdown fix was actually to split the page table into 2. One which was the PML4 here, which was reserved for the kernel after the meltdown fix, and one for the user, which was created for the meltdown fix. And let's have a look at the first one. And we talked about this self-referential entry. We have this memory address here. In Windows 7, the topmost page table has a very special entry at offset F68. It's this one. it's self-referential. It actually points to the page table itself, the PML4 itself, and the memory manager uses this. And IF68, it's actually this one. And it, as you can see, it's in little endian, so it ends with 67. It ends with 7, and 7 in this case means that it's present, it's active, it's writable, and it's accessible from user mode. And that shouldn't be. It should only be accessible from the kernel itself. But this is the kernel view of things after a patch, so it might not be that catastrophic. So let's have a look at the user page table as well. And if we check the offset at F68, the self-referential entry in this one, it also ends with a 7. And this is the issue itself. So the total meltdown vulnerability was really one single bit set in error. And if you read the Intel manual, it clearly states that user supervisor, if 0 user mode accesses are not allowed to this memory region, so it's set to 1 user mode accesses are allowed. Exploitation, it was so easy, I don't even want to call it an exploit. It was just a matter of inserting a fake page table entry at a fixed address is in already mapped in process virtual memory. Once I inserted this fake page table entry, I could read and write to the arbitrary physical memory that that page table entry pointed to. Another use case that I didn't expect at all was cheating in games. It turns out that anti-cheating software, it's really powerful pieces of software. They detect most, if not all, software-based cheats. And a hardware-based cheat, it should, in theory, it should only be seen as a PCI Express device on the gaming system. And you kind of need to have PCI Express devices in your gaming systems. You need to have a powerful graphics card and things like that, for example. And then you could use this hardware device and then ship memory to a remote computer and do the analysis there, and the anti-cheat software cannot reach into that computer. You could do things like read-only, wall hacks, radar and map the cloak hacks, for example. You could do the analysis on this separate computer and ship the player location to another computer, for example. You could also do writing, but that might be a little bit more easily detectable if you're tampering with the in-game internals. I first became aware of this summer last year when there was a big cheating scandal in the Norwegian CSGO community. It turned out that people had been cheating at home and on LANs to which it was okay to bring your own computer. And then a couple of months later on, even a cheat-focused fork of my PCI Leech software appeared on GitHub. And this is how it looks like. If we look really closely here, we'll see that we have the PCI Express Screamer FPGA board inserted in this gaming computer. Initially, anti-cheats didn't catch this at all, and it was kind of touted as the next generation of cheating, the future of cheating. But ICEA, which has a really good anti-cheat, it didn't take them that long to catch up, and when they catched up, they wrote a blog entry about it on their site geared toward the gaming community, where they explained you might have a DMA device in your computer, you read the memory, ship it to an attack PC, do the analysis there, and then you ship the player location to a phone, for example. They claim that prices for these cheats have been selling in the range of $1,500 to $5,000. And of course, when they started to do detection, it was really simple initially for them to do it, since most people had just been downloading my default bitstream of the FPGA firmware from my site, and there was some hard-coded vendor IDs and device IDs in there. So if you had them in your gaming system, you were probably a cheater, right? So just ban them. So it resulted in a ban wave of both cheat customers and developers. But now they also claim that they're able to detect hardware-based cheats even with disguising the cheat as a legitimate device. And they're can look into some other things, some other telltale signs in there, which is quite easily detectable, which is not so easily be changed by the user or the cheater. But what if it was possible to perfectly emulate a legit hardware device? And this is kinda in the last couple of months already been demonstrated by researchers at Cambridge University in their Thunderclap paper. They used a really expensive hardware setup here, around $4,500, but were able to emulate some networking card entirely in software. And I don't know, maybe it will be, we will see this in the gaming area in the future as well. But let's continue with the memory process file system, the memory analysis part. When I was creating it, I wanted to have something that's really easy for users to use, but it should yet be very powerful. I wanted to create something that was really modular in design and had plugin functionality. APIs for C was given, since it's coded in C. And I also added Python API, since Python is really popular within the security community and also in the memory forensics community. And of course, performance is super important when clicking around in a file system. You can't really wait for 1 or 2 minutes for a directory with the files to render. It needs to be pretty much instant. This is what I came up with. And I used a really awesome third-party product, which is called Docan. Which is a user mode file system. It takes care of all the hard parts, so I don't have to do it. It has a kernel driver for the file system parts. All I need to do is to implement some really simple user mode hooks in the memory process file system executable. This really simple callbacks is pretty much, it's just a thin wrap around the main analysis library, which is where I do all the memory analysis. It's a really big C API. It also takes care of all the memory analysis steps, and it's in here I do the translation between the physical memory and the virtual memory. For example, I need to know a little bit about different memory models. Also have a plugin manager in there for Python and C plugins. And if I do use a Python plugin, I want to call back in this memory analysis library, and I do that via the Python API. And if you code your own Python applications, you can use this Python API as well. And then I had a separate library for physical memory analysis, and it's the Leech Core library, which has a really strong focus on physical memory reads and writes. That's all it does. And this allows me to separate memory acquisition from analysis in a really nice way. And it supports a lot of different memory acquisition methods. I do support the hardware-based memory acquisition methods, and then we can do writing to memory as well. Also, I do support live capture of physical memory from a system, either by using PMEM or even better, MathSwish awesome Dampit tool. And we might want to analyze memory dumps as well. And then you can do that by clicking on a file, for example, a raw memory dump file, a full crash dump file, for example, created with Dampit, and even Hyper-V save files. Recently, I also got a really nice contribution from Synactive. If you do have a vulnerable HP ILO interface, you might be able to reflash that one with a special custom firmware, or even implant DMA backdoor in a live HP ILO system without reflashing it. And once you do have the DMA backdoor in there, it's the BMC of HP servers, and then you can read and write memory from the host operating system running on this server using these tools. You're also able to connect to a remote agent, a remote leech agent, over a Kerberos secured mutually authenticated RPC. And this remote agent is pretty much the Leech Core library, but remote, so you can use any of the above memory acquisition methods over the network, but on that remote system. The main analysis library, it looks something like this. We do have an API on top in which my memory process file system is using, or your own application. And on the very bottom, I do capture physical memory from the Leech Core library, but I also have a simple object manager in there, which allows me to handle some simple objects in this library, and that allows me to, in a really good way, have caches for physical memory and the page tables, which are in two different caches. And then I have a layer which translates physical memory into virtual memory. And I need to have a knowledge of a few different memory models in order to do that. And then I have a notion of a process object, which contains a memory map object and a module map object. Also have a plugin manager there, which allows me to communicate with external plugins. And if you're capturing live memory, volatile memory from a live system, either using the FPGA or dump it in its live KD mode, I do have a background updated thread in there as well in order to update the caches in the background so the user don't have to wait for the memory capture. And of course, I do all the analysis in here as well. So imagine you have an incident response scenario. You might have a suspicious process on a remote system, and that computer might be quarantined to a VLAN or something like that. And it's quite often you do have limited bandwidth and high latency over the networks, corporate network. You want to analyze physical memory maybe, and a full memory dump over the network might be super slow. The solution might be to retrieve only the memory you actually need to analyze, and analyze it with the memory process file system. Or even better, it's possible to run the analysis on the remote computer by submitting a small Python script. So let's do another demo. Let's demo some remote malware memory analysis. I'm going to analyze live malware memory from a remote system which has been infected, and we're going to analyze this memory by just clicking on some files. So this remote system is another Hyper-V machine here. So I'm going to start this Leech agent. And we do have this memory address here. I'm using dump it with its live KD mode in order to capture live physical memory from this remote system. And I'm going to do it in interactive mode here today, and also in insecure mode. Since this computer is not connected to an Active Directory domain, I can't really secure the connection with Active Directory Kerberos. So let's do it in secure mode, which it basically allows anyone with network access to connect. So let's initialize the connection to this remote system. We're going to start the memory process file system using the dump it device to capture memory from this remote system. So these memories should be mounted now. So let's click into having a look at it. Can click into the names folder, and I already know what the malware is. It's an old Citadel example here. You can have a look at its memory map, for example, and we'll clearly see that we have some read, write, execute sections with the malware, which is this one. But we can analyze its memory. We can open the virtual memory in a hex editor, and in the hex editor I already know what to search for here. So let's search for some known really good antivirus software here, because this malware has a block list for antivirus. So we can see, and this is like live memory by just editing a file, live memory from the remote system captured. And when we are doing this, we are only capturing that piece of memory. And if we were doing this analysis with the FPGA as well, we could even hit save here after we changed something, and the malware might not even notice, since we are not using any APIs on that remote system really. So having incident response, there's really big advantages doing physical memory analysis, and you might already be familiar with Stardust by Matt. If you're not familiar with it, please have a look at it. Or you might even use the more traditional approach with volatility. Both those tools are super awesome. And the memory process file system is not really meant to replace them. It's more meant to act as a platform to do things with your own favorite tools. It has an okay performance, even over laggy networks. And if you use the agent, you can actually do the remote analysis part directly on the remote endpoint, which is super nice since it avoids both latency and bandwidth. And future focus for is to do even more performance optimizations. I do wish to parallelize things even more in order to further reduce latency. And having a multi-threaded design is really awesome here, since it allows me to do things like background process refreshes. And the analysis capabilities is a little bit limited at the moment, but I do plan to add more in the soon future. So let's have another look at the Python API. Let's analyze the live memory from this remote system in Python by using the API. Let's locate read-write executable sections in the remote memory. Let's switch over to Python here. First, I need to import the Python API. Can have a look at the functionality here. We have a few functions that we can call into. We're going to initialize this first. We're going to connect to this remote system. And let's connect to it. And if we check the remote system, you see that we connected. And we are still connected with the other connection from memory process file system. So this agent supports multiple connections to this remote system. And now we're able to do things like retrieving the PID for a process name, for example, the cmd.exe as this PID. And we can retrieve some additional information for that process, or for all processes, and have a look at it by PID. And here we see things like the process name, we have the address of the process, the PEB, and a few other things in here, which might be interesting. When we have this information, we can retrieve it for all processes. We can iterate over it, and we get a really nice list of all the processes in this system. We can retrieve the memory map for a given process. And this is just one entry in the memory map. It would be huge if I would print it, the whole one. It seems to be a page from the anti-DLL, which seems to be read execute here. And it's the anti-DLL here. And now when we do have all this information, we can do code a small Python program. And let's, for each process in the system, let's iterate over it. And for each process, we are going to retrieve its physical memory map. And let's iterate over each entry in this memory map to see if we can find some read-write executable entries in there. And then we're going to print it on the screen. And I'm only going to print maximum 2 entries on the screen per process, just for show here. And now it takes some time. It's a lot of memory to acquire from the remote system, but it's quite fast anyway. And now we went through all the paging structures of all the processes on the system, and it's already finished, as you can see. We seem to find some read-write execute pages in OneDrive, which is pretty normal. We have our Trojan executable here, and also have some pages in PowerShell, which is kind of normal as well. We can also retrieve virtual and physical memory by using the API. And then we do it by using the memory read function. And the first argument is the PID of the process we wish to retrieve the memory from. But we can retrieve from physical memory if we use PID -1. And yeah, it looks something like this. But even better, we might be able to do this by analyzing live memory on the remote system by submitting a short script to that remote system and do the analysis on the actual remote system, and then we don't have to acquire any memory at all. And it's really nice in low bandwidth scenarios. So let's have a look at our small program here. It's pretty much the same as I ran before, but now I'm printing all the entries from the whole memory map. So let's use the PCLH program with the agent exec Python program to submit this small script to the remote host. So let's still use dump it to do the memory acquisition. I submit the script, we wait for the result. It should, and we already have it. And all the memory analysis in this step it's been done on the actual remote system, and by analyzing physical memory on that remote system, we are not really relying on any operating system APIs to do this. And this makes it really hard to catch as well. So the Python API looks something like this. We have memory read functionality, memory read and write functionality. We can both read physical and virtual memory. We can retrieve various kinds of process information, listing the PIDs, for example, retrieve which modules, which DLLs are in the specific processes. And for the DLLs in the each process, we can retrieve exported functions, imported functions, sections, and things like that. And then the whole file system, even though it's not really mounted as a drive, it still exists in the API world, so we can query the API and read and write these virtual files still. So when I was creating this, performance was super important. I'm really happy to have completed multi-threading, since it's a huge boon, since it allows me to do a lot of things in the background, which doesn't really affect the user. I also rely on in-memory caching and some really intelligent parsing in there. An example of parsing, I really want to avoid scanning large chunks of memory for known signatures if I can avoid it, because reading a lot of memory is expensive in terms of performance. One thing how I achieve this is when I'm starting the memory process file system, I need to locate the kernel directory table base, which is the base of the virtual memory paging structures for the kernel, so I can translate physical memory into virtual memory and the kernel base itself. And it might already be known to the underlying device. If it's known to the underlying device, I can use that, of course, then we are done, nothing more like that. Otherwise, I can check for a memory structure, which is called the low stub. It's something that usually exists at the address 1000 in physical memory in hex. It doesn't have to, but it usually does. And special with this structure is that at offset A0, you do have the kernel PML4, the directory table base of the kernel, which then would allow me to translate virtual memory into physical memory. And then I have a pointer to the base of the to the entry of the Antus kernel at offset 70. It's not the base, so I need to be scanning back a few pages, but it's not too much memory, so it's really quick. And as a last resort, I might to go for scanning as well, but it takes a little bit longer time, so I want to avoid it if I can. So let's do another demo. Let's do some writing to live memory on another system as well, and let's overwrite memory in a process on another system. So for this part, I'm going to use the vulnerable Windows 7 here, since the total meltdown vulnerability allows me to do writing to physical memory as well. So let's start the leech agent, and I'm going to start it in interactive and in secure mode here today. And I'm starting the notepad here with some text as well. So let's try to, I need to mount this remote. So let's mount the file system. It's mounted. And now we should be able to click into it. And we can go into the notepad process, for example. And in here, we do have the virtual memory, but more interestingly, we do think that this text, hello opcode, it should be somewhere on the heap of the notepad, I would suspect at least. And in the vmem D subdirectory, we have for each physical memory region, we have enumerated it as a file as well, so it should be kind of easy to access, and is tagged if we find what the memory is, it's also tagged with that. So let's try to do it, and let's do it in Ubuntu. So let's first mount the drive, and then we go into that subdirectory. And let's have a look if we can find the heap in there. It's probably on the primary heap 0, and we just have one memory region for this heap. And let's do a simple strings on the heap. We're going to do strings, and the text in Notepad is stored in little endian, so UTF-16. So let's use strings in that mode, and just grep for hello, and we have the text there. Hello opcode in this file. And this is memory acquired from this remote system live now. And let's try to change that text into something else. Just use our hex editor to do that. And let's search for that memory. So this is the text hello opcode in UTF-16 little endian. And here we do have some promising text here. So let's try to change that text into something else. And hit save in our hex editor. And the text didn't change. And that's because we need to just update the frame buffer. We can just click anywhere, and the text will be updated. So thank you. So imagine doing this on another system using the FPGA hardware, for example. It might be useful in some research scenarios, I hope. So the memory process file system, it's a work and a lot of future work. It's a work in progress, and a lot of future work remains. One thing I want to do is quite soon is to add some page hashing of the pages, which would allow me to, I think, reduce amount of memory I capture from remote systems, and also to do things like low bandwidth cache coherency updates. I wish to add a lot of functionality and features quite soon, and additional analysis capabilities, primary ones being support for the Windows registry and also threading. Threads of the target system, analyze those ones. Support for non-Windows operating systems, it's certainly possible, but it's a lot of work, and that's a little bit more far in the future. And of course, additional memory acquisition methods is always nice. But to sum everything up, the memory process file system, it's an easy point-and-click file-based memory analysis tool. It comes with an API for C, C++, and Python. It has a wide range of memory acquisition methods, not just hardware-based ones, but software-based ones, and also this remote agent. It's 100% open source, and it's found on my GitHub. And thank you very much.